In this presentation, stormwater management is addressed not merely as a technical drainage issue, but as a multidimensional subject that must be considered from the perspective of urban planning and ecological resilience. The title, Blue-Green Infrastructure for Stormwater Resilient Urban Planning, already suggests that we need to rethink how water is understood in the city. The aim here is not to remove rainwater from the system as quickly as possible, but to retain it within the urban environment, slow it down, filter it, reuse it when appropriate, and at the same time generate public, ecological, and spatial benefits. In this context, the presentation discusses the transition from gray infrastructure to blue-green infrastructure, European policy frameworks, different implementation tools, scenario comparisons, and the institutional issues encountered during implementation. In this way, stormwater is positioned as a strategic field that connects engineering and planning, ecology and design, and policy and practice. This content slide shows how the lecture is structured. First, it explains why stormwater has now become a matter of strategic planning. Then, conceptual frameworks such as WSUD, SUDS, LID, BGI, and nature-based solutions are introduced. The following section focuses on how different interventions, scenarios, and design options can be compared. This is followed by implementation constraints, governance, maintenance, and issues of institutional coordination. Finally, selected case examples and key takeaways for planning practice are presented. This structure is not simply a course outline that transfers conceptual knowledge, it also offers a systematic learning flow for decision-making, design development, and the transition to implementation. In other words, the topic first defines the problem, then introduces the conceptual tools, explains decision support mechanisms, and finally connects them to real planning practice. This slide presents the learning objectives. The first objective of the presentation is to explain why stormwater management has become a strategic ecological planning issue. The second objective is to interpret European Union climate adaptation and nature-based solution frameworks. Third, it is expected that students understand how GIS, BIM, and parametric design tools can be used to compare risk scenarios and planning options. The fourth objective is to support the selection of multifunctional blue-green measures for different urban contexts and scales. Finally, the presentation emphasizes the importance of advocating participatory, interdisciplinary, and inclusive implementation pathways. Taken together, these objectives show that the lecture does not aim only to provide information, but also to develop analytical thinking, design-based decision-making, and a planning attitude. Therefore, the presentation establishes an integrated teaching structure that supports knowledge, skills, and attitude together. This slide explains why stormwater has become a strategic planning problem. With urban growth, impermeable surfaces such as roofs, roads, and parking areas increase, which causes rainfall to flow more quickly into drainage systems rather than infiltrating into the soil. As a result, runoff speeds increase, peak flows rise, and existing infrastructure systems come under heavy pressure. Especially when older combined sewer systems cannot handle this burden, flooding, pollution, rising temperatures, and habitat loss occur together. In other words, the problem is not only about removing excess water, it is also about land use, resilience, environmental quality, and governance. For this reason, stormwater must no longer be treated as an invisible infrastructure component, but as a planning issue that directly shapes urban space. This is why district-scale, multifunctional, and spatially integrated solutions are now needed. Here, the conventional gray drainage approach is compared with the blue-green ecological planning approach. The main objective of gray systems is to move water away as quickly as possible. This approach is mostly based on a pipe-centered, invisible, and single-function infrastructure logic. In contrast, the blue-green planning paradigm sees water as a resource that should be retained, slowed, infiltrated, and, when possible, reused. The spatial logic changes accordingly. Instead of being hidden underground, the system is integrated with public space, open green systems, and landscape design. This shift is important because blue-green systems do not only reduce flooding, they also provide cooling, biodiversity, spatial quality, and everyday urban comfort. In addition, they are more suitable for phased retrofits, corridor-scale thinking, and future-oriented resilience. Therefore, what is discussed here is not a minor technical adjustment, but a conceptual transformation in the way cities relate to water. This slide presents the policy and framework context of the topic. The European Green Deal promotes climate-proof and resilient urban development, while the EU adaptation strategy treats nature-based solutions as a cross-cutting priority. The Biodiversity Strategy 2030 emphasizes urban nature, restoration, and ecological connectivity. In addition, the Floods Directive and the Water Framework Directive connect river basin management with flood risk management. Local adaptation plans and urban nature plans translate these broader frameworks into site and project-scale action. For that reason, stormwater interventions should be justified not only as drainage infrastructure, but also as multifunctional initiatives related to climate adaptation, ecological restoration, public value, and long-term urban policy. This part of the presentation shows that planning decisions must be grounded not only in technical performance, but also in policy alignment and institutional legitimacy. This slide compares different ecological approaches and terminologies. Flood risk management focuses primarily on hazard reduction, whereas water-sensitive urban design offers a more integrated framework that links water to urban sustainability. SUDS and LID emphasize source control and distributed runoff reduction. Blue-green infrastructure and nature-based solutions broaden the framework even further by bringing biodiversity, spatial quality, public benefit, and resilience together. These concepts are related, but they do not mean exactly the same thing. For that reason, it is important for planners to know which language is more appropriate for which scale, governance setting, and project objective. In some projects, flood safety may be the priority, while in others, city-scale ecological connectivity and multifunctionality may be more central. Therefore, choosing the right concept is not only an academic distinction, it is also important for project framing, funding language, and institutional cooperation. This slide summarizes the co-benefits of blue-green infrastructure. The fact that one intervention can simultaneously reduce flooding, improve water quality, provide cooling and shade, support biodiversity, enhance public space quality, and create visible urban ecology makes blue-green infrastructure especially valuable in planning. However, these benefits do not emerge automatically. Whether a system is truly multifunctional depends on where it is located, the quality of its design, the sustainability of its maintenance, and its connection to wider hydrological and ecological networks. In other words, a single rain garden or one green roof does not automatically generate a holistic ecological benefit for the city. The key issue is whether these measures are connected and made functional within the urban system. Therefore, the value of blue-green infrastructure must be understood not through isolated objects, but through its capacity to operate as a network and deliver multiple benefits at once. This slide presents the main risks and constraints that must be managed during implementation. At the physical level, soil conditions, groundwater, slope, and contaminated land may all become limiting factors. At the spatial scale, land competition, existing underground infrastructure, and limited retrofit space may create major challenges. Operationally, maintenance access, sediment accumulation, or vegetation failure may reduce system performance. Institutionally, fragmented departments, scattered budget structures, and unclear responsibilities may hinder implementation. Socially, uneven distribution of benefits, temporary disruption, or safety concerns may also emerge. For this reason, stormwater planning is not merely a matter of technical sizing. It also requires the joint management of land use, interdepartmental coordination, maintenance arrangements, and public acceptance. This part of the presentation clearly demonstrates that even a technically correct solution can fail if it is not supported institutionally and socially. This slide shows how scenario analysis can be carried out using GIS, BIM, and parametric tools. In the first stage, the catchment is mapped by identifying impermeable surfaces, slopes, flow paths, and exposed assets. In the second stage, the baseline condition is modeled to determine runoff patterns, overflow hotspots, and service gaps. In the third stage, alternative design options are generated at the street, block, and district scales. In the fourth stage, these options are tested in terms of hydrological performance, cost, co-benefits, and maintenance. In the final stage, the most balanced solution portfolio is selected and an implementation pathway is defined. The key point here is not that digital tools make decisions on their own, but that they make the decision process more visible, comparable, and iterative. This approach allows planners to evaluate multiple design combinations at once and make evidence-based rather than purely intuitive choices. This section explains the logic of multi-objective decision-making for intervention portfolios. No single measure can simultaneously optimize runoff control, low cost, low land take, high biodiversity value, and strong public benefit. In addition, the performance of a layout may change depending on rainfall characteristics. The hydraulic relationships between measures also shape the final result. For this reason, robust planning does not search for one perfect object, but rather for acceptable and balanced trade-offs. This is exactly what a portfolio logic means. In other words, decision-makers should evaluate not individual devices in isolation, but combinations of measures that work together. This approach is also closely related to economic evaluation. A solution that appears strong in cost-benefit terms may still be insufficient if it performs poorly in relation to other objectives. The main message here is that good planning is usually based on hybrid and context-sensitive sets of solutions. The Measure Toolbox slide shows that each intervention has a different hydrological role, spatial footprint, and maintenance profile. Green roofs are effective in dense areas for source capture and cooling. Rain gardens provide water quality benefits and visible landscape value along street edges. Swales and wadis are strong for conveying and infiltrating water in linear systems. Permeable surfaces can delay peak runoff in street retrofits, but they require regular maintenance. Water squares and ponds provide public storage and flood safety, while also creating a strong spatial identity. Rain barrels and cisterns offer reuse potential at the parcel scale, but they are limited when used alone. The main idea here is that no single technology is appropriate in all cases. Planners need to think in terms of a toolbox and select interventions according to context. In particular, the strong economic performance of wadis in the Oslo case makes the value of these linear landscape systems even more visible. This slide explains the core design principles of multifunctional systems. The first principle is to capture water as close as possible to where rain falls. The second principle is to connect measures into a treatment train, meaning that runoff is slowed, cleaned, and stored step by step. The third principle is to treat drainage space as ecological corridor space that can also support biodiversity. The fourth principle is that these spaces should function not only during extreme rainfall events, but also under everyday urban conditions. What is being described here is that good blue-green design is not simply a matter of placing several technical elements side by side. The system should be established as a connected spatial network extending from roofs to streets, from pocket parks to receiving systems. Such an approach strengthens both hydrological performance and public support. People tend to value and care more for places that create everyday benefits, not only spaces that become meaningful during emergencies. This slide discusses economic evidence through the Grefsen case in Oslo. It compares benefit-cost ratios and shows that wadis in particular achieve the strongest ratios. Separate sewer systems also generated high values, while mixed strategies combining rain gardens, rain barrels, and wadis produced more moderate but still positive outcomes. The importance of this section is that it moves the discussion from principles to investment logic. As emphasized in the presentation, economic evaluation is not a calculator that automatically produces absolute truths. It is a decision support tool that makes visible which costs and which benefits are being counted. CapEx, OpEx, and present value analysis make it possible to compare costs and benefits that occur at different times. In addition, the Oslo example shows that strategies designed for less frequent but more intense rainfall events can generate greater benefits. The main lesson here is that economic value should not be read only in terms of engineering performance, but together with spatial suitability, maintenance capacity, and long-term resilience. This slide highlights governance, maintenance, and participation. Many solutions that appear technically sound fail to perform as expected when post-installation maintenance is neglected or when responsibilities are unclear across institutions. For that reason, cross-departmental coordination, shared budgets, common standards, and city-scale learning from pilot projects are crucial. On the maintenance side, lifecycle budgeting, ownership clarity, access arrangements, and post-installation monitoring are all important. From the participation perspective, neighborhood priorities, co-design processes, and an environmental justice lens must also be included. This is because a system is only successful in the long term if it is supported, maintained, and socially accepted. Therefore, the task of planning is not only to select the right measure, but also to establish from the beginning the institutional and social conditions that will enable that measure to keep working over time. The context fit matrix summarizes which measures are more suitable under different urban conditions. In dense centers and retrofit streets, measures such as green roofs, rain gardens, and water squares become more prominent. In larger residential areas, a broader combination of interventions becomes possible. In peri-urban catchments, larger linear systems such as swales and wadis show the strongest fit. At the small catchment or parcel scale, rain barrels and limited-scale solutions become more meaningful. The purpose of this matrix is not to propose one universal solution, but to build contextual intuition for decision-makers. Since every urban area has different land conditions, densities, open space capacities, and institutional constraints, the choice of measure must also vary accordingly. In larger settlement areas, it becomes easier to produce meaningful combinations, whereas in smaller areas more precise and carefully targeted choices are required. Therefore, selecting the right measure depends not only on technical performance, but also on reading the urban context correctly. The implementation roadmap presents the main steps that can guide planning practice. First, outcomes need to be defined. These should include not only flood safety, but also ecological value and public benefit. Then, risks and opportunities should be mapped by considering hydrology, land conditions, biodiversity, and user needs together. In the next step, alternatives should be prototyped and scenarios should be modeled. After that, implementation should be structured in phases, and investment decisions should be linked to maintenance plans. The final step is monitoring and adaptation, meaning that lessons learned from pilot applications are used to refine and scale up the system. The key message here is that pilot projects only generate strategic value when they are documented, monitored, and translated into institutional standards. In short, the roadmap combines technical design with institutional learning in the transition from idea to implementation. The best cases slide presents two complementary messages. The Grefsen case in Oslo compares different strategies economically and shows which measures can produce higher benefit-cost ratios. In particular, the strong performance of wadis demonstrates that blue-green solutions can be not only technically feasible, but also socially and economically valuable. The Beijing and Copenhagen pilots, on the other hand, show how cities can move beyond purely pipe-based systems toward multifunctional water landscape systems. The key lesson from these examples is that co-benefits do not emerge automatically, but must be intentionally designed. They also emphasize the importance of addressing both small and large rainfall events, establishing clear water management priorities, and integrating stormwater and landscape design from the beginning of the process. In this way, these cases show how economic analysis and institutional learning can work together. The final slide summarizes the main takeaways of the entire presentation. First, stormwater should not be seen only as a hydraulic problem, it is also a spatial, ecological, and governance issue. Second, good blue-green systems should not only slow water, but also support biodiversity, improve public life, and produce everyday urban value. Third, implementation should be collaborative, phased, and open to learning. Digital scenario tools, pilot projects, and participatory mechanisms are what turn promising ideas into durable planning practice. Therefore, the overall logic of the presentation can be summarized in 3 phrases. Think systemically, design multifunctionally, and implement collaboratively. If these 3 approaches are brought together, stormwater management can become not only a risk reduction tool, but also an opportunity to build a more resilient, livable, and ecologically integrated urban future.